The ratio test is the last convergence test that we're going to be dealing with. It's also the one that kind of a lot of people have the hardest time with, but it's kind of straightforward in a lot of ways, so it's not the worst, personally. So the ratio test, let the summation from n equals 1 to infinity of a sub n be our infinite series. So our series, so the summation from n equals 1 to infinity of a sub n, will converge if the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n is less than 1. So if I take the limit of the next term divided by our current term, or our current term divided by our previous term, if that is equal to, or is less than or equal to 1, then we are good to go, it converges. On the other hand, if we have that same exact thing and it's greater than 1, our series is going to diverge. So if we have the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n is bigger than 1 when we take it, it's diverging. Now, the last part here, it's inconclusive when the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n equals 1. So if we get that it equals exactly 1, that means it is inconclusive. And this is the one scenario, the one time that if you were to tell me, cry and try something else, that would be accurate. The reason why, in order to show what we have, we're going to have to do a lot of algebra. We're going to have to work through a bunch of things in order to do this, which means it's going to take up some time. So when you get it equal to 1, having to now do something else is sad. So if we get it equal to 1, we have to do something else, which means cry and try something else. So determine if the following series converges or diverges. So we have the summation from n equals 1 to infinity of 2 to the n divided by n factorial. So we have a sub n is equal to 2 to the n divided by n factorial. Reminding ourselves factorials are something multiplied by itself. So n times n minus 1 times n minus 2 all the way down to times 3 times 2 times 1. N plus 1, we are looking at 2 to the n plus 1, so we're changing n to n plus 1 now, times n plus 1 factorial. So we need to make sure that we have parentheses there. If we don't, then we're going to have n plus 1 factorial, and this is not the same as that. This would be n, and we add times 1, so plus 1. So in this case, if I said 5 is n, this would be 5 plus 1 factorial, which would just be 5 plus 1. This, on the other hand, would be 5 plus 1 factorial, which would be 6 factorial, which would be 6 times 5 times 4 times 3 times 2 times 1. And those are a little bit of a different number. So now we need to look at those two, but in a limit form. So we're going to take those two things and put it into our limit. So the limit as n approaches infinity of our two things. So we have the absolute value of. On the top of our fraction, we're having n plus 1, so 2 to the n plus 1 divided by n plus 1 factorial, dividing it by a sub n, so 2 to the n divided by n factorial. So now we need to figure out what this would be. So one of the first things that we're going to do is we are going to move it around. We're going to multiply by a reciprocal instead of dividing two fractions. So we have the limit as n approaches infinity of 2 to the n plus 1 divided by n plus 1 factorial times, we're multiplying by the reciprocal, so I'm going to flip that bottom fraction. So we have n factorial on top divided by 2 to the n. Okay. So normally what we could do is multiply these two together, get it into one fraction, but what we are going to do instead is we are going to simplify it so that way the like things are in similar fractions. So we have the limit as n approaches infinity of the absolute value of 2 to the n plus 1 divided by 2 to the n. So I'm keeping these two together into our fraction, top and bottom. And we're multiplying that by n factorial divided by n plus 1 factorial. Okay, now is when we need to do some simplifying. So we need to simplify two fractions here. We need to simplify 2 to the n plus 1 divided by 2 to the n. And we need to simplify n factorial divided by n plus 1 factorial. So let's start with what we have here. 2 to the n plus 1 divided by 2 to the n. We can think about this in a couple different ways. One of the ways that we can think about it as 2 to the n plus 1 is the same thing as 2 to the n times 2 to the first divided by 2 to the n, which means that we have 2 to the first, and that's it. The other way we can think about it is when we divide fractions like this is like taking 2 to the n plus 1 and subtracting n from it. This gives us 2 to the first, just like we did. Either way works. We just need a way. So this first part, we have the limit as n approaches infinity of the absolute value of 2 times. We have n factorial divided by n plus 1 factorial. So to keep in mind factorials, we're multiplying each term from each other. So we have n times n minus 1 times n minus 2 and so on. So if I were to do the same thing with n plus 1, this would be n plus 1 times n minus 1 times n minus 2 and so on forever. Well, if I look at just this part here, if I look at just at this part in on, this is the exact same thing as n factorial. So instead of writing all of that, I can just say n plus 1 times n factorial. I have an n factorial on top and an n factorial on bottom, so this is going to be 1 over n plus 1. So we have 1 over n plus 1 times 2. So we have the limit as n approaches infinity of the absolute value of 2 over n plus 1. And if we think about our rules here, we have a Bobo case bigger on bottom, so this is going to go towards 0. That's fine for us because 0 is less than 1. When we are less than 1, our series is going to converge, so the summation from n equals 1 to infinity of 2 to the n divided by n factorial converges.